everybody. So today we're looking at multiplying polynomials. All right, so let's put some examples up on the board and we'll see what we can do. All right, so here are two up on the board. Why don't you pause the video and see what you do, and then play after you solve it, and we'll see if we get the same thing. All right, so for this first one, we have a monomial, which is one term, times a binomial, which is two terms. Polynomial just means many terms, so we could have one, we could have two, we could have three, we could have whatever many we want. But here we go, let's go ahead and do this. So what we're going to do is we're going to distribute that x into each term here. So you might have seen like the rainbows before, but they're not rainbows. We're distributing. So x times 3x gives us, what, 3x squared. Then we get x times negative 4 is negative 4x. All right, that's what we should be getting. Let's move on to number 2. Same idea as we're distributing, but what we're doing is we're distributing each term in the binomial to each term in the other binomial. So that looks like this. 2x times x gives 2x squared, and then 2x times 4 is plus 8x, and then negative 3 times x is negative 3x, and then negative 3 times 4 is minus 12. And then we combine our like terms. There's no x squared term, and here we have some x terms. So 2x squared, let's see, 8x minus 3x, we get plus 5x, and then minus 12, because there are no other constant terms to combine here. So this one, there's no constant, no like terms to combine, so look at that. Now, you might be asking, holy cow, this is such a strange way to multiply. Who would have done this? Well, this is actually how we multiply when we learn in like 3rd grade or 2nd grade, whenever we learn how to multiply. This is actually the same thing, just looks so different. Impossible, Salim, you say. Impossible. No, not impossible. Check this out. Let's do this. Example 3. All right. Here you go. Go ahead and multiply 19 times 3 like you did when you were a kid. So pause the video and then try it yourself. Okay, we're back. So you probably did, or many people do, how I was taught was 3 times 9 is 27. Regroup. And then you do 3 times 1. But that's not 1, that's 10. 3 times 10 is 30 plus 2. But that's not 2, that's 20. So it's 3 times 10 plus 20 gives us 50. So 57. So you're saying, well, geez, Sal, that's nothing like this. It literally is nothing like that. Well, it's actually the exact same thing. It's just packaged a little differently. So here we go. We have this. I wrote it differently so that it looks like what we have up here. So now we do the same kind of distribution. 3 times 10 is 30. And that 3 times 10 is right here. 3 times 10. And then 3 times 9, there's 27. So we're going to add 27. And that 3 times 9, that was the first thing we did here. And now we combine these terms and we get 57. Great. So there you go. We related the old way we multiply to how we multiply binomials like this, or polynomials like this. Impossible that there's any relation between this and what I've done in the past. Impossible, you might be saying to yourself. Let's see what we can do. All right, here's a 2-digit multiplication problem. Try this for yourself. Pause the video, try it for yourself, and then we'll come back. See what we get. All right. So here we are. We're back. So if you're like me, you were taught this way. 9 times 1 is 9. Great. 9 times 2, that's 20. So 9 times 20 is 180. And then 1 times 1, but that's not 1, that's 10. So 1 times 10 is 10. And then 10 times 20 is, last time I checked, that's 200. We add these together, let's see, 9, 399. Great. All right, so let's see if we can relate this to something like we did here. So I'm going to write this multiplication problem similar to how we did here. And so 20 plus 1 is 21. 10 plus 9 is 19. So now we're going to multiply, we're going to distribute like we did up here. So 20 times 10, I'm going to do that first, even though that was one of the last things we did. 20 times 10, which is 200, which is right here, 20 times 10. And then 20 times 9 is, what's that going to be, 180? So we're going to add that, which we did here, 20 times 9. And then we're going to do 1 times 10, which is plus 10, which we did right here, 1 times 10. And then we're going to add in 1 times 9, which is the first thing we did in this method. And we add them all up, and we should get the same thing. Whoops. Let's see, 200 plus 180 is 380, plus, let's see, 10 and 9 is 19, and then sure enough, 399. Yay, look at that. So we related the old way we learned to multiply with the way we generally multiply, in this case, 2 binomials. All right, I'm going to clean up the board, and then we'll get some other samples up here, and then we'll do the same kind of thing. Ah, there we go, much better. Okay, so here's some examples. Pause the video, try them for yourself, and then we'll come back and check how we did. All right, so let's go ahead and do this. Number 5, we're going to distribute each term across. So let's see, 3x times x is 3x squared. 3x times negative 1 is minus 3x. Negative 10 times x is minus 10x. Negative 10 times negative 1 is plus 10. Combine our like terms. All right, so there we go. 3x squared minus 13x plus 10. All right, there we go. All right, let's look at example 6. X minus 5 quantity squared. That means it's x minus 5 times itself. And then we're going to distribute in the same way. I'm not going to make the distribution marks. I'm just kind of, I want you to show you, I'm going to show you a way that what I do to keep track of myself. X times x is x squared. X times negative 5 is negative 5x. Moving over. Negative 5 times x is negative 5x. Negative 5 times negative 5 is plus 25. And then we combine our like terms. There we go. All right, so there we go. We get x squared minus 10x plus 25. So there we go. We did some multiplication of polynomials, and we related this funky multiplication method. I've heard it called funky by some students before, sometimes other names. But we related this method to the way we oftentimes learn how to multiply back in elementary school. All right, bye.